Okay, so again, what we noticed here is that as time goes on, the spacing increases. And that's an important feature of this kind of motion. So to start off, this is what your motion diagram should have looked like. Okay? This is what your motion diagram should have looked like. I've got 5 dots for the 5 different times, 0, 1, 2, 3, 4, and they are located at t equals 0 is at 0 meters, 1 second at 1, 2 seconds at 4, 3 seconds at 9, and 4 seconds at 16. Okay, and then I've got these arrows that connect it. Right, so just checking in. This is what your motion diagram should look like. I'll just give you a minute to make sure yours looks like mine. Right, and you can see what Mariella described, that the length of the arrow gets longer every second that goes by, which means we went farther every second. Now, the other thing we can figure out is how long each one of these displacement arrows is. Okay, so let's go through the 4 of them. Let's start with the first one. How long is that first displacement arrow? From t equals 0 to t equals 1. Dana, how long is that? 1 unit, because we went from 0 to 1, so we do like 1 minus 0. So it is 1 meter long. Okay. When I go from 1 second to 2 seconds, how long is that arrow? Okay, how long is that arrow? So we go from 1 to 2, so it's 4 minus 1. So the next one is 3 meters long. Okay. Let's look at the one from 2 seconds to 3 seconds. How long is that arrow? Okay, so we go from 4 to 9, so that would be 5. And then finally, 3 seconds to 4 seconds, 7. So we again, 16 minus 9 gives us 7. Okay, so now that we know how far we go and we know the time that it takes, we can figure out how fast, on average, we're going in each of those 1 second chunks of time. So that's what we want to do next. Okay. So the first chunk, all we have to do is take those numbers and divide it by 1 second. So that's really easy. So the first chunk is average velocity is 1 meter per second. Then 3 meters per second, 5, and 7. Okay, so to get to the average velocity, we just took the length of the arrow and divided it by the time. And what was the time interval, the delta t? So between the first one, from t equals 0 to t equals 1, by how much time goes by? From t equals 0 seconds to t equals 1 second. How much time is that? 1 second, right? Between 1 second and 2 seconds, how much time is that? 1 second, right? So that's where why the numbers look similar, but the unit is different, because we've divided by 1 second. This would be the average velocity, what we did yesterday.
It's not always going to be meters, right?
For the most part, we will be using meters when talking about this, but it could be centimeters or miles or kilometers or inches, right? It's the unit of the dimension length divided by dimension time. So here's what I want to do now. I want to think about how does that average velocity change? From, let's say, we know between 0 and 1 second, it is 1 meter per second. And then between 1 and 2, it's 3. I want to write down how much does it change by. Well, so you're saying the 1, 3, 5, 7, you think that's an exponential, you're saying. Okay, so let's see. Let's go through step by step and see how much does the average velocity change by. So one way to think about that is, okay, it starts moving 1 meter per second, and it needs to end up moving 3 meters per second. So what do I have to either add or subtract to 1 to get the 3? I'd have to add 2 meters per second. So that means between, let's say between 0 seconds and 2 seconds, sort of at the halfway point, it's like maybe not clear when this happens, but we'll be able to explain that better in a second, that I have to add 2. That's the difference between 1 meter per second and 3 meters per second. It would be plus 2. Let's think about that for all of the other times. So if I go from 3 meters per second to 5 meters per second, that's also plus 2. And when I go from 5 to 7, that is also plus 2. Okay? So this blue arrow that you can add to your diagram is showing what we might call the velocity difference, or as a symbol, delta V. The delta tells us change of how much the velocity changed at 1 second, at 2 seconds, and at 3 seconds. Tatiana.
When you're doing a velocity difference, there will be a pattern.
Possibly. We're going to see 2 different patterns. Well, we're going to see for most situations either that the delta V is 0 or that the delta V is a constant number. It's possible that delta V could have been 2 and then 4 and then 6 and then 8. That's allowed, but that's not what we're going to be studying.
So will either be a constant number like 3, 3, 3?
It'll always be constant, but it'll either be 0, which is like a special constant, or in like this case, it's 2. Okay, good question. But in the world around us, it's a number that's allowed to change. So, for example, I don't know if we have baseball fans in the room, but like when a player tries to steal from first to second, when they start off, they're not moving, they have no acceleration. Then they start to speed up. Then they reach a maximum speed, so they stop speeding up, and delta V becomes 0, and then they have to start slowing down, and delta V becomes negative, right? So it is something that can change. We'll limit ourselves to situations like this. Okay, but let's go back to Meryl's observation. She anticipated that the change would be exponential, that every second that went by, the change would become a bigger and bigger number. Now that we've done it for the other times, we see that it's not increasing, it's a constant. Every second that goes by, we're adding 2. We had 2 meters per second, add 2 meters per second, add 2 meters per second. So let's say we went to t equals 5. Let's make a prediction. If we were at t equals 5, what would v be equal to? So what do you think?
9.
Yeah. So we would add another 2. If we went to t equals 6, we'd add another 2. What would it be then? 11, right? So this pattern would just continue. Okay. The distance, however, that we travel is going to get bigger and bigger over time. So that's where we're going to see a curved graph. If you made your graph of position versus time, you'll see that it is not a horizontal line or a straight line. It is a curved line. That's where the curve shows up in the position part, but not in this velocity part. So if we want to go the next step and say not just how much did the velocity change, but how much did it change per time, what would be my next step? How do I turn this into per time? What math should I do? Sort of. How did we go from position to velocity? I figured out the change in displacement and I divided it by something. What did I divide it by? Time. So I'll do the same thing here. If I divide how much I changed my velocity by the time that it took, I'll get the time rate of change of velocity. Okay, so what would I divide these numbers by? How much time should I divide them by? Joe, what do you think? How much time goes by between every dot? 1 second. So I would take these numbers and divide it by 1 second. And that's how I would end up with this thing called the acceleration. All right, let's take some questions now before we go to the next slide that kind of summarizes all of that. Do you have any questions about what we've done so far? Tajan, any questions about what we've done so far? So we're going to, so I'm going to show you in a second. The idea is we want to not just know how much it changes by, but we want to know the rate. Every second, how much does it change by? Now, because we've drawn this every dot a second, that math part is easy. Dividing this by 1 second, what would we get? If I do 2 meters per second divided by 1 second, what would that be? Again, we got to be careful when we divide a fraction. It would be 2 meters per second squared, right? It's why we practiced it at the beginning of the year. This is where we're seeing it now. Okay. So let's summarize that. So here I have, if we take the time rate of change of velocity, that thing is called acceleration. And it's the same kind of steps. You find the 2 points, the time and how fast, and its velocity at t1, you do it again at t2, you subtract and you divide. And that thing is called acceleration. Right? And so we'll add to our motion diagrams an arrow that shows the acceleration. I'll make a habit on my slides to draw in blue so we can see the difference. If you could do that too, that'd be cool. If you have 2 different pens.
Wait, so when you subtract 0 minus 1 and then 1 minus 2.
So it's not the positions now we're subtracting, it's the velocities at those positions. So I would be subtracting not 0 and 1 for position, I'm subtracting 3 and 1. That's the difference here. And then once I subtract the 2 velocities, I subtract the 2 times, and then I divide. So the change in velocity divide by the change in time. Our acceleration, the amount of time that goes by. So delta V, how much the velocity changes, divided by delta time, how much the time changes. And you'll notice acceleration also has a direction, right? As you see, it's drawn on the diagram there. We'll take a look at what it would mean if it was in the opposite direction in a second. All right, so I'll give you a minute to finish copying this. Similarly to average velocity, average acceleration doesn't care about what you do in between, right? It only cares about the beginning and the end of what you pick. So I could move and run and go back and forth and do all crazy stuff, right? But it would only care about the beginning and the end, just like average velocity only cared about the first and the second. Okay. Now let's think about what it might mean if, well, first, what would the acceleration be if the velocity stayed the same? If v1 equals v2, what would the acceleration be equal to? Asia, what would it be? 0, right? If the two things are equal and you subtract them, you'd get 0 and the acceleration would be 0. And that's going to be true whether it's moving at a constant velocity, whatever that number is. Maybe it's 5 meters per second and it just continues doing that. Or if it was at 0, if it wasn't moving and it stayed not moving, that would also be an acceleration equal to 0. Okay? So your acceleration could be 0 whether you're not moving at all or you're moving at a constant velocity. Let's flip this around and take a look at what about if we were sort of traveling in the opposite way. So here is my motion diagram. I'm going now from right to left, and you can see how the times have been flipped. What's different? Well, first, what's kind of the same about this motion diagram? What's one thing you see that's the same? Sort of. Well, let's do 0 and 1 again. So from 0 to 1, we go from 16 to 9. So that would be -7 because we're going to the left. Then we go from 9 to 4. That would be -5. Again, the negative sign just means we're going towards the left. 2 to 3, and then 3 to 4. Okay. Then if I want to turn that into velocity, what do I have to do? If I want to go from the displacement to the velocity, what should I do? Really, what should I do?
Figure out how much the speed change between.
Before the speed change part, first we need to know the velocity. So we need to divide our displacement by something. What do I have to divide by? The time that goes by. So how much time is there in between each dot? 1 second. From 0 seconds to 1 second, that is 1 second of time. From 1 to 2, that's 1 second. So it's 1 second for all of these. So now I have -7 meters per second, -5 meters per second. Okay. And we would keep going. Now we're at the point where we want to find the difference in the velocity. So what order should I subtract these? We'll do from the 0 and the 1. To do final minus initial. Deborah, what's the final velocity? Which of these two is the final? -5. It's the second one, so it's final, so -5. Okay. Minus -7. Okay. -5 minus -7. What does that turn out to be? Milo, what is that? Okay, so the difference is 2 meters per second, positive 2. All right. And then if I want to turn that into acceleration, what do I have to do next? Divide by what? How much time should I divide it by? How much time? 1 second. Okay. So I get that the acceleration is 2 meters per second squared. What direction does it point? Left or right? It's a positive, so it points to the right. So now I have an example where the velocity and the acceleration point in opposite directions. Before they were pointing in the same direction. How is that? What does that mean for us looking at this motion? We have the velocity and the acceleration pointed in opposite directions. What is the thing doing? Every second that goes by, what's happening to its speed? It's slowing down. So if the acceleration and the velocity are in opposite directions, we slow down. If they're in the same direction, we speed up. Okay, and this diagram shows you that. Every time you draw one of these green arrows, it's getting shorter and shorter. You find the acceleration, it points in the opposite direction. -7 plus 2 is -5. -5 plus 2 would be -3 plus another 2, -1. And we get back what we know those velocities are. Okay? So this is something we're going to continue to look at over the next week, that relationship between the velocity and the acceleration, when they're in the same direction and when they're in opposite directions. You get this interesting result. Okay? And then our eventual goal is to explain why that happens. Why do you get an acceleration? That's for our next unit. Now we're just describing the motion. But that's where we're going. Okay. The next thing I want to look at is, what if we wanted to make graphs or graph this acceleration? Okay. So we found, let's do our original example. Here I would put my acceleration versus time, and I'll mark off 1 second, 2 seconds, and 3 seconds. And we found that the acceleration was equal to 2. And it was 2 at all of the times that we observed. Okay, so how is this graph? Yeah. So in our example, our acceleration stays a constant. It stays 2. And graphically, what that looks like is this horizontal line. Okay. And tomorrow, we're going to say how you can go from this graph of acceleration to velocity, and then how to go from velocity to position. That's what we'll do tomorrow. Okay. But this is what a graph would look like for constant acceleration. It's always the same number. In our example, it was always 2. Okay. And just to give you sort of a preview of that, if we wanted to make a graph of velocity and time, we'd end up with something that looks like this. The velocity, every time we go by, is increasing by 2. And so the connection in this direction from velocity to acceleration is figuring out the slope. You can see it because we said acceleration is the change in velocity divided by the change in time. And that looks just like a slope formula. Right? So like I said, that's what we're going to focus in on tomorrow. But I want you to maybe start seeing some of those connections. But again, the big observation is that the acceleration is a constant. In our case, it was 2. All right, so I want to leave some more time today for you to do an example problem. So basically what I want you to do is repeat the analysis we just did together, but for a different situation. Okay, so you're not going to get the same value of the acceleration, but you're going to follow the similar steps. So here's your data. You've got these 5 data points and what the positions are. You're going to make your motion diagram. You're going to make that plot. I want to get you familiar with what that plot looks like. Then you need to figure out the average velocity, like we did together, and then determine the average acceleration. So you've got 12 minutes to work on it. You can work together on your whiteboard, but put things in your notes as you're going along. Yeah. Okay.
That's due tomorrow.
Okay.
Yesterday, and there's 2 questions that are like the same, but I did not understand how.
Okay. So there's the difference between speed and velocity. Speed, you figure out the distance and divide by the time. Velocity is the displacement and divide by the time. So look back in your notes about the difference between speed and displacement. And I bet that's the reason why you're like, you feel like you get it, but you're not getting it. That's the slight difference. So one has to do with distance and one has to do with displacement. You're welcome.